So anyway, you take this, we have some potassium chlorate. We're going to heat the potassium chlorate to cause it to decompose. Can anyone guess what one product is going to be?
Oxygen.
How do you know that?
Because
It says so in the lab. Okay, or in the question. So we're going to make some oxygen. Would anyone like to take a stab as to what the other product is? CO2 is not one of them, especially since there's no carbon. What's left?
Chloride.
And? There you go, potassium chloride, which is also a solid. So, all you do, take some potassium chlorate, heat it, it is going to decompose into oxygen gas and another salt, potassium chloride. Okay? We need to collect that oxygen gas. Here's how we're going to go about doing it. Now, you guys may remember me showing you this and how I tried to describe how a barometer works by using this. Does anyone remember that? I filled this up with water, turned it upside down, okay? Well, we're going to do a very similar thing. Here's another piece of equipment that I didn't have you guys learn. I had you cross it off. It was called a gas collecting bottle. Does anybody remember this on there? Okay. This was on there also. And all I've done is filled it up with water. And when I say filled it up with water, I mean filled it up with water. Now, with the udiometer, remember I just used my finger to close the hole when I turn it upside down? My finger's not going to work here. So a lot of times you use like a glass plate. Okay, so you use a glass plate, turn the bottle upside down, you put it in the trough. Okay? So now it's incredibly similar to what I had done with the udiometer. So now we need to put our little glass bottle over here. Okay, so there's our little glass bottle that we have also filled up with water. So we got water everywhere. Okay, moving on. Now, that's where the gas is going to end up. How are we going to make that gas? We're going to take our little handy dandy ring stand, put a burner on it, light the burner. Okay, put a little flask right here. And inside that flask, we're going to put some, let's say potassium chlorate. I use purple for potassium. Any significance to that? What's that? Yeah, the flame test. Remember potassium ended up being purple? Okay. Not that potassium chlorate's purple, but anyway, that was kind of fun. Now, by heating this, we're going to generate some oxygen and some chlorine. Oh, by the way, what's wrong with this picture here?
Not balanced.
Yeah, it's not balanced. Anyone balance it yet in their head?
2, 3, 2.
Good. 2, 3, 2. Awesome. Nicely done. So by heating this stuff, we're going to create some oxygen gas. That oxygen is going to go up through here, but we want that oxygen. So what we're going to do is put a stopper in this, and in that stopper, we're going to have a hole. And in that hole, we're going to put a little piece of glass tubing. Okay. So now the oxygen is being directed out the glass tubing. Well, we need to get that oxygen from here over to here. Any suggestions? Another piece of equipment that I showed you earlier this year.
Yeah, a hose.
Hose, a rubber hose. Okay, so we're going to take a rubber hose, and we're going to take that hose and bring it over here, and then we're going to take, there we go, put that over here. And so now the oxygen gas that's being generated is going to go up into the hose, over here. And now what's it going to do when it gets up there? The oxygen gas. It's going to go up, forcing the water out. So the water level is going to decrease to some extent. And we're now going to have some oxygen gas molecules in there. Cool, huh? Nice handy little way of generating some oxygen gas if we need it for some other process. And so there we go. Now, here's where the issue comes into play. Could we measure that volume? Sure we could, okay? But here's the problem. $225 milliliters of water are in that beaker. We come back Monday. Is there still going to be 225 milliliters of water in that beaker? Why not? See a lot of people shake their heads. Evaporates. You mean water evaporates?
Yeah.
Like just on certain times or all the time? All the time, right? Now, what if the temperature actually increased in the room? What's going to happen to the amount of evaporation? You think? Increased. What do you think? What if the temperature decreased in the room? Very likely. What do you think is going to happen? Decrease. So it's temperature dependent. You guys are all fairly clear on that, right? Okay, good. Water constantly and always evaporates in an amount that it evaporates at different rates depending on the temperature. If I did this process, is it just going to be oxygen gas up here? Or might there be another gas up there? Why?
Because it evaporates.
Because there's water here, right?
Yeah.
So there's also going to be a small amount of water vapor. Water vapor is a gas, right? And that gas takes up some space, doesn't it? So when I measure the volume of the gas that's up there above that liquid, it's mostly oxygen, but some of that space, some of that volume is taken up by the oxygen or the water vapor. We need to somehow or other account for that and get rid of the water vapor. Does that make any sense? In order to find out how much oxygen we actually collect. So here's how we're going to do that. There's this concept. You do need to add this to your notes. I'll give you guys like 8 seconds or 18, whatever it takes to get your notes out. There's this concept that was named after, once again, an old dead guy called Dalton's Law of Partial Pressure. Okay? And it essentially says this. In a mixture of gases. Now, can anyone think of a mixture of gases that you might be familiar with? Air. Wouldn't air be a mixture of gases? What is, I know we've had this conversation, what does air consist of mostly?
Nitrogen.
What was that again? Nitrogen. Nitrogen. Does anyone remember the percentage?
It was hot 70s.
It was like 78. That's okay if you didn't remember the exact number. 78% nitrogen. What's the next biggest component? As it turns out, it is oxygen. Does anyone remember the percentage of that?
21.
It is 21. 21 plus 78 is 99%. So of the other 10, 12, however many other gases are in there, they only make up 1% of the rest. Carbon dioxide is like 5th or 6th on the list. It's a really small percentage. And that goes into, you've heard the whole thing about how much carbon dioxide we're pumping into the atmosphere, the whole global warming thing and everything. The reason it's an issue is carbon dioxide only makes up a very small percentage of the air that we have. So if we pump more stuff in there, it has a greater effect. Does that make any sense? Because it's only such a small percentage anyway. So there you go. There is a mixture of gases. Well, let's assume that air is let's just call it oxygen and nitrogen, okay? And if we knew the pressure of each of those components, if we added up the individual partial pressure of each of those components, we would come up with the total pressure of the mixture of gases, which should make a little bit of sense. Here's an analogy that I like to use. It's not a perfect analogy, but I think it works for you guys. Let's imagine that you all are gas particles, and you're in this room. You're taking up space in this room. And you guys are actually a mixture of two different gases. What gases are you? Well, we have male gases and we have female gases, right? Okay? And you're all intermixed together. You're all taking up the same, filling up the space. You're all not interacting with each other to form other gases. Okay? You're just existing as if the rest of you don't exist. However, so it's like the air, it's like nitrogen and oxygen, and it's kind of like this scenario here where we've got oxygen and water vapor existing in the same space. We need to get rid of one of those components. Okay, so let's subtract the male gases. Okay, so somehow or other we're going to get rid of you males. Okay, you're the smallest component in this room. That's why I decided to get rid of you guys. My other group was the girls. So anyway, we get rid of you guys. Now the volume is the pressure exerted by the females is less, and the volume taken up, well, stays the same actually, but the pressure's less. Okay? So that's why we're looking at the partial pressures. Now, what if you knew one of these? We know the total, don't we? Don't we know the total pressure? Okay. What if we knew one of these components? Let's say we know this component. How can I find this? I just kind of gave you a hint. Subtract, right? Okay. So we just need to know the other component. Well, we don't know how much oxygen's in there. However, as you guys already discovered, you guys know that water evaporates. You also know that water, the rate of evaporation depends on the temperature. Scientists have known this for hundreds of years themselves. In fact, this is very accessible information. In fact, it's so accessible, you have the information. On the very first periodic table that I gave you guys, remember that one? Had the names, the atomic, it had everything on the periodic table, right? But on the back of that periodic table were three charts, three tables. One of them was the ion chart. We spent a lot of time with that. The other chart we didn't spend as much time with. That was the activity series. Does anybody recall that? Using to predict whether a single replacement reaction is going to occur or not. And the last chart, which Keegan is currently looking at, is called the water vapor pressure table. If you guys could please pull out that table. So in our little lab scenario that we have going on here, we have a mixture of gases. It's oxygen plus H2O. That is going to be equal to the pressure of both the water individually and the oxygen individually. We know the total pressure. It's 755 torr. What's a torr otherwise known as? Millimeters of mercury, okay? And do we know the pressure of water at 25 degrees Celsius?
23.8.
It's 23.8 torr. And so if we know this, we don't know that. Would you agree?
Mm-hmm.
How are we going to find that?
Subtract by 23.
By subtracting the 23.8. And that's going to give us the pressure of our oxygen. Does that make any sense? Ladies, you see why you did that now? Okay. So, when is it that we're going to have to subtract the water vapor pressure from the total pressure? Under what set of conditions? This is the very first thing I had you highlight from the question. Collected over water. Anytime you see that phrase, a gas collected over water, you're going to have to subtract the water vapor pressure from the total pressure. Does that make any sense? Okay, so that's the clue. That's the clue when you see that. You see water, subtract water. Okay. As it turns out, I think this comes out to 732.2 torr. Somebody can check me on my math on that.
Second.
You good?
Is it 731.2?
It might be 731.2. In fact, I think it is 731.2. All right, here we go. Now, we almost have all the components we need. Is there anything else that needs fixed up here? Somebody please say yes.
Convert to Kelvin. Is that what it is?
No, we're going to convert to kelvins.
Kelvin.
This comes out to be 298.2 kelvins, and this turns out to be 273.2 kelvin. Everyone hunky-dory there? Now it's just a matter of plugging and chugging. So here's our handy-dandy little equation we're going to use. And it's just a matter of plugging everything in that we have. So we have 720 milliliters times, currently it's the 731.2 and 273.2 over 760 torr times 298.2 Kelvin. And obviously you've already seen what the answer is because I provided that for you, but it would be good for you to verify that by making sure that you know how to do this with your calculators. Did you guys all get 564? What'd you get again? Boom, 635, right? Awesome. Very good. All right, once again, couple of things to be learned here. One, we now are aware of Dalton's law of partial pressure, okay? And we are going to apply Dalton's law of partial pressure when we have a gas collected over water by subtracting the water vapor pressure from the total pressure. Pretty straightforward process, you just have to be aware of that now.